Okay, so what the function says about this radical. So we want to start off by looking for symmetry. Is there symmetry in this? As in, what is the function at negative x? Okay, so composing this, I get negative x square root 2 minus negative x, which would be negative x square root 2 plus x. And can you see from looking at this and this, not the same, so it's not even. Factor the negative out, and it's not going to be odd either. So this one has no symmetry. And the next thing we're looking for is asymptotes. I guess we could look at a limit to infinity to see if there's a horizontal asymptote, but can we all agree that there's no vertical asymptote? You're taking a root function that's got some kind of reflection and multiplying it by x, and you're not going to get a vertical asymptote. So you might have a horizontal asymptote. How do you know? You look at the limit as x goes to infinity. And as x goes to infinity, this gets big, this gets big, and can you see that this is just going to keep on getting infinitely bigger? There is no limit to infinity. It's not going to approach any value. We're going to be multiplying this by a number that keeps getting infinitely larger. If I put a positive x in here, in fact, this must have some kind of domain restriction before we start. Maybe it would help if we started there. What's our domain for this function? What's under the radical has to be greater than 0, as in 2 has to be bigger than x. So for all of this function, there's the domain. Okay, so when I'm looking for this limit to infinity, in fact, we can't go to infinity, but we could go to negative infinity. So now this might make more sense. I'm going to be multiplying this by a negative large number. Negative times a negative is going to be as a positive. I take the square root, and then it's going to be a bit smaller, but we're still getting an infinitely large number, positive multiplied by a negative. This function is going to keep on going down, 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 down. There is no horizontal asymptote. So we've got no symmetry, we've got no horizontal asymptote, we've got no vertical asymptote. What do we have? Do we have intercepts? So we have this domain, x is smaller than 2. Intercepts. If I let x equal 0, I guess y is 0. Okay, well there's something I can graph. I've got that point 0, 0. I guess the other point that would be 0 is if x is 2. If x is 2, y is 0. And we can all just see that, doing that in our head. Yes? Okay. Okay, so there's our two intercepts, and we already talked about the domain, and I think we'll do the range after we graph this. In fact, it'll be easier to see the range once we know what the maximum value is. Okay, so that's pretty much everything from the function, and let's look at the derivative. What's f prime at x? Oh, I'm going to keep track of a t-chart as we go, because I'm finding later that I look at those numbers and then I can't find all of them. Okay, so the biggest x could be was 2. And I'm going to keep going down. I might have to fit things in between. We'll see. Okay, so I've got those 2 points for sure. Okay, the derivative of this. So I need a product rule. So my function x times 2 minus x to the 1/2. So using a product rule, it's the first function times the derivative of the second, 1/2 times 2 minus x to the negative 1/2, chain rule times the derivative of the inside function, plus the derivative of the first function, which is 1, times the second. And let's factor this. Let's factor out the 1/2 and the lowest power of 2 minus x appearing, which is negative 1/2. Okay, so I factored out the 1/2, I factored out the 2 minus x to the negative 1/2, and I'm left with a negative x plus. I factored out a 1/2 and I need a 1, so that becomes 2. I factored out a 2 minus x to the negative 1/2, so this will be 2 minus x. Okay, so no negative exponents. The 2 goes in the denominator, the 2 minus x to the 1/2 goes in the denominator, and this is going to be 4. And I've got a minus x and a minus 2x gives me minus 3x. So 4 minus 3x and 2 square root 2 minus x. So here's my first derivative, critical numbers. Would be x is equal to, well, I guess 2, because I'd get a 0 in the denominator, and 4 over 3. Okay, so I already know that at 2 is where my function starts, which is why I've got a critical number there, because it's just going to stop at that point. And 4/3. So let's just set up a little interval and check where's the function increasing and decreasing. And there's 2, and here is 4/3, or 1 1/3. And if we can find a max or a min. Okay, we're not going to go bigger than 2 because this is the end of the road here. This is the domain for the function. We can only look at values less than 2. So between 4/3 and 2, what is the number between 4 over 3 and 2? 5 over 3? 2 is 6 over 3? Okay, so if I put 5/3 into this function, the denominator is always positive. It's a square root. If I put 5/3 in, I'd have 3 times 5 over 3. It's going to give me a 5. 4 minus 5, it's going to be negative. And 4/3 down. Okay, is the number smaller than 4/3? Something easy. How about we take 0? The denominator is always positive. If x is 0, I've got a positive. So the function went from increasing to decreasing. That tells me that 4/3 is my local max. Okay, so just to keep this all straight, we're going to just say our intervals. Our intervals of increase are from negative infinity to 4/3. Our interval of decrease is from 4/3 to 2. We've got a local max at x equals 4 over 3. Okay, so this is an important point. Let's put this in here. So if x is 4/3, we're going to have to calculate a y value. I'm just going to tell you, I already did it. It's about 1.1. Okay, so right here when x is 4/3, so 3/3, right about here, we've got a local max there. And then we just need to know where this function is concave up and where it's concave down. So let's take the second derivative. Okay, so here's our first derivative, f prime. So looking at that, let's take the second derivative. Do I want to do that with a quotient rule? Yeah, probably. So I'm going to square the denominator. That is 4 times 2 minus x to the 1/2 squared is going to give me 4 times 2 minus x to the power of 1. Okay. And then we've got low, 2 times 2 minus x to the 1/2. Derivative of the top, which would be times -3, minus the top, 4 minus 3x, times the derivative of the bottom, which is going to be 2, pull the constant out in front, and then take this derivative using the chain rule. 1/2, 2 minus x to the -1/2 times -1. I'm just going to zoom this in while we clean up this algebra. Okay, so here's some easy things to simplify. 2 times 1/2 is going to give us 1. And this negative times this negative is going to turn those into positives. This might make this a little bit easier. And so what are my common factors? I've got a 2 minus x to the -1/2, and it looks like that's it. Okay, so bracket 2 minus x to the -1/2, and it's going to go into here, 2 times -3, -6 times 2 minus x to the power of 1. We got this plus 4 minus 3x. Got that, got that, got that. Oh, done. All over 4 bracket 2 minus x to the power of 1. Negative exponent, this is going to come down. So I'm going to get 2 minus x to the 3/2 in the denominator. So denominator, 4 bracket 2 minus x to the 3/2, because 1 plus 1/2 gives me 1.5, or 3/2. And simplifying this, I've got -12 plus x plus 4 is giving me a -8 minus 3x, which was, so I had a 6x minus 3x leaves me with 3x. Double check that just to make sure that you've got that second derivative correct. Okay, so what are my critical numbers here? Well, they would be x is equal to 8/3 and x is equal to 2. Is 8/3 in the domain of the function? No. So not in domain. Therefore, just ignore it. So we're just looking from -infinity to 2. The denominator is always positive. We're taking a square root. If I put in a number from 2 down to infinity, let's try 0. I'm going to get a negative here, which tells me that this function is concave down all the time. Okay, so I think we're ready to graph this. A function that's always concave down, and this is a local max, is going to look something like that. No inflection points. There's no change in concave.